This is the answer to Chapter 1, problem number 65 from the Smith Organic Chemistry textbook. And this problem asks us to convert a series of molecules that we're given formulas for into Lewis structures. And so the formulas tell us a little bit about the connectivity, and we can take it from there. For example, when we see CH3, we should know by now that that's going to be a carbon with 3 hydrogens around it like this, and then bound to the next carbon in the chain, which is a CH2. So it will have 2 hydrogens. And then the next carbon, it says COOH. So that's going to be a carbon double bound to one oxygen and single bound to the next oxygen, which is bound to a hydrogen as well. And then to be a true Lewis structure, we do need to just put our lone pairs in. So put them around the oxygens. If this is difficult for you to do just by looking at it, you can follow the formula that we used for earlier problems in this chapter involving drawing Lewis structures. So you can lay the molecule out given the connectivity that the formula gives you, and then connect everything by single bonds, count the number of valence electrons, see how many connecting by single bonds takes care of, and then complete octets wherever possible and assign lone pairs. However, you do want to get good enough at this that you can look at a formula and sort of skip all of that and get to the point where you can look at the formula, see how the molecule is laid out, and draw the Lewis structure for it. And so that's what I'm going to do for each of these. So again, B starts with a CH3. So that looks like that. Then it's CON. So that's going to be C, double bound to oxygen, single bond to nitrogen. The nitrogen has a hydrogen. And then we go back to carbon, and it's another CH3. So just to verify that this is right, take a look at everything, make sure that everything has its complete octet. And we do need to put our lone pairs in to make these correct Lewis structures. So there they are. And so that's B. So then we'll proceed to C. So again, it starts with a CH3. CO is going to be C double bond O. CH2Br. C H2 Br. And then again, we do need to include our lone pairs. So there's C. For D, we have CH3C OH. So that should tell us that we're going to have a central carbon with an OH and 3 CH3s. And then again, lastly, let's put our lone pairs on the oxygen. So moving on to E. E is very similar to D. So again, it's a central carbon with 3 CH3 groups around it. And then C double bond O, single bond H, and again, got to put in the lone pairs. F, CH3COCl. So we can start once again with the CH3. By now, you should know that when you see a CO, it means C double bond O, and the chlorine. And lastly, the lone pairs. Ooh, and you know what? This looks like an H, and that I suppose could be confusing. So let me just fix that quickly. That is not an H. That is a double bond. Okay, and the last two I'll put on another page to avoid having a crowd. So G, again, starts with a CH3. And we have CO, which again, by now you should know, means C double bond O. Then a CH2, CO2H. So C, when you see CO2, it means this type of structure, H. And the lone pairs. All right, let me just fix this H so that it looks like an H and not an N. There we go. And that's G and H, the final one. HO2, CCHOH, CO2H. So the beginning of this is written backwards because you do want it to show connectivity a little bit. So it's just written like that so that we know that it's the oxygens that are bound to the carbon. So that's what those first three letters there mean. Then we have a CH. With an OH. And then a CO2H. So that's gonna look like this. Okay, and then we just need to put our lone pairs in. So like that. And that's the answer to part H. So remember, the way to solve these is to get the connectivity from the formula, and then just make sure that everything has a completed octet, and make sure that you're including your lone pairs for a good Lewis structure. And that's the answer to chapter 1, problem number 65.